Hello everyone and welcome back. Today I will talk about why you should learn the mathematical parts of general theory of relativity. When I tell people that I am studying currently the mathematical structure behind general theory of relativity, people's reaction is why? Don't you already know it? Didn't you take a GR course? Well, the answer to that question is yes, I already took a GR course, but you see, in those GR courses, of course, it is very mathematical. And for newcomers, especially, tensor products and some primitive language about differential geometry seems very frightening. But unfortunately, in many of the introductory physics courses on GR, many of the differential geometric parts about Einstein's relativity is left behind. And this is done because these parts are quite exotic and dangerous for a newcomer, because you probably would get lost if you are introduced in that part of the field. And in a way, differential geometry's development in the 20th century has been heavily influenced by general theory of relativity. So without general theory of relativity, we wouldn't have probably this many of the aspects of differential geometry that we already have. So it accelerated our understanding of differential geometry, since it gave us a physical intuition and in a way somehow to test these abstract objects in a very concrete way, since we can connect to a physical intuition. And that is a very good and I think very informative example of how physics and mathematics can influence each other very well. But of course, some professors and physicists see this kind of differential geometric applications of general relativity as a misstep in the evolution of the field, because if you want to understand the current literature in GR, you need to be able to understand differential geometry very well. And many of the theorists currently who are working on some of the fundamental questions in GR, for example, for definition of mass, ADM mass in GR, it is currently an open question. So, in a way, if you truly want to understand the current developments and the primitive questions that arise in general theory of relativity, you need to understand the mathematical aspects of it. And understanding differential geometry takes time because it requires a very advanced knowledge of linear algebra as well as topology. So in a way, you need to have certain kind of mathematical maturity to attack these kind of problems. So you don't just apply your known techniques in physics to those of differential geometry. So they are quite foreign to physicists at a first glance. And the book that I follow is by Piotr Kurystiel, whom I met at Tübingen in 2024. And Piotr Kurystiel is one of the leading experts of the field, but there are many incredible physicists who look from the mathematical lens of GR. And I believe it all started with a French mathematician, Jacques Brouhat. Probably I'm mispronouncing it, but unfortunately I'm not French. But Brouhat introduced, I believe, for the first time the Cauchy problem to general relativity, and she was the one who rigorously predicted the existence of gravitational waves in GR. So she's a bit of a flag bearer in the field. And after her, Dimitrios Christodoulou, one of the students of John Wheeler, is one of the the continuation of this kind of tradition of applying mathematics to GR. And I believe that he actually worked with Brouhat in France in his postdoctoral studies. So in a way, currently there are 20 to 30 physicists who are working on this field very religiously, and they formed a cult of physicists. So everyone in this small field knows each other, and Crucial is part of it, the book I showed you, and it is highly mathematical. It's a very introductory book, so you can grasp ideas on it better. But for example, if you want to understand a very primitive concept of GR, this isn't the book. So the purpose of the book and the purpose I'm reading it, because I mean, while you're reading it, for example, there was a definition about like how since I mean in a locally, for example, there was like an argument in Sylvester's inertia problem, which says that under smooth coordinate transformations, the eigenvalues of your metric always is constant. So in a way, I mean, its signature is always constant. So these kind of predictions have a direct realization in the physics of it, but in order to understand the mathematical background of it, you need to read it. So in a way, while I'm reading it, I don't learn new stuff about physics. I'm learning how can I translate this language that I know already in physics to mathematics, and how can I, for example, maybe get a physical intuition from otherwise unknown territory in mathematics and how these interact. And while reading this kind of mathematical books that are written for mathematicians, actually, of course, for mathematicians who want to learn physics. So by reading this kind of books, you can also practice your mathematical notations and your mathematical intuition in general. So thank you. This was the video. Thank you for your time, and stay with physics.